Okay, can everyone see all right now?
Yes, we can see very well.
Okay, perfect. So yeah, again, just as a bit of an introduction, my name is Tyler Gleckler. I gave a talk here a few months ago now. The topic for the talk was also about nanoscience and nanotechnology, but it went into a little bit more detail that I probably should have avoided. And this time, we're going to focus a little bit more about how nanotechnology and nanoscience can help with environmental repair and preservation, which is obviously a hot topic right now and something that's very important. Um, Last time I also went a little bit farther in terms of how much I was speaking, and this time I'm interested in hearing as much as possible from you guys. So at any point, feel free to interrupt me, ask a question, or if you'd like to just leave them at the end, that's fine as well. I tried to keep it somewhat brief so that we have all the time to talk about this further. So the official title of the talk is Using Nanoscience and Nanotechnology for Environmental Repair and Preservation. So going back to sort of what was just being covered in the introduction about what is nanoscience and what is nanotechnology, again, as was so brilliantly explained, the nanoscience is sort of revealed in the name. Nano is the prefix for billionth, so 10 to the negative ninth for any of you who like thinking in numbers. So we're talking about extremely, extremely, extremely small dimensions. And one thing that kind of puts that into perspective nicely is if we consider a sheet of paper, still very, very, very thin. A sheet of paper is actually 100,000 nanometers thick. So 6 orders of magnitude, many, many incomprehensibly larger than one single nanometer. So when we're talking about nanoscale materials and technologies, we're talking about really as small as we can get before we get into particle physics and a bunch of physics and chemistry that's well beyond my pay grade. So therefore, nanotechnology is simply just the application of nanoscience for our use. It's the use of matter on the atomic, molecular, and supramolecular scale to do all sorts of different things. And what it really comes down to is that when you have materials and technologies at this scale, you create all sorts of new and interesting properties, which has led nanotechnology to have applications that are very, very wide ranging. We're talking about as broad as from televisions to cancer treatment and really everything in between. And as I'll discuss in a little bit more detail later on, is this whole field is really in its infancy. It's at the very beginning. Much of what we're going to talk about today, specifically in terms of environmental science, isn't being rolled out in reality in many cases, sadly. But over the next several decades, we expect to see all of these things come to fruition and so much more that we probably couldn't even imagine today. So sort of then why nanotechnology? And the answer to that question comes down again to those new and unique properties that are created when you make materials that are so small. So again, it has a huge range of applications, including for environmental science, as we'll go into more detail with today. And that's for primarily two more technical reasons. Again, I won't go into too much detail, but just in case for those of you who are interested, or at least to make sure everybody has a sense of the big picture, it's for two reasons. The first is that nanoparticles and nanomaterials have what's called a very high surface area to volume ratio. So if you picture each one of these nanoparticles as little spheres, little globes, the entire surface of that sphere is tremendously larger than the total volume, the total space contained within each one of those spheres. And what that actually means really is that the nanoparticles are highly reactive, which in chemistry, typically higher reactivity makes life a little bit easier and gives us a little bit more flexibility. So that's something that will come up again and again. And that's particularly for catalysts or materials that make chemical reactions go and easier and with lower energy. The second reason, apologies, is for quantum effects that take place on the nanoscale. So once we get to the very, very small, the size of atoms and molecules, this is where quantum physics starts to take place. And physics creates its own new little rule book that we're still learning more and more about regularly. And this creates many, many interesting things that we can tailor into new technologies. So some of the environmental applications that we're going to talk about today, and there are more, include sustainable energy production. So whether that's solar is one of the more notable ones. It applies to wind energy and others. There's also water purification. and then combating climate change through reducing greenhouse gas emissions. And again, we'll go through each of those a little bit more carefully. But the point is that in general, many different innovative nanoscience is being used to harness many pressing environmental issues and contribute to global ecological preservation. So this is probably familiar to everybody, but I think it's worth just highlighting and emphasizing and giving some context. Again, the reason this is so important is because the problem we have across the world in terms of climate and the ecosystem. So breaking that down broadly in terms of, again, climate and the ecosystem. For climate, we're mostly talking about climate change. So this is what's happening as a consequence of excessive greenhouse gases, with the greenhouse gases being carbon dioxide, water, methane, but carbon dioxide being the one that's arguably most important and the one that we all know the most about. And this is leading to climate change, and it was previously called global warming, but now climate change. So the accumulation of these gases in the atmosphere essentially acts like a blanket for the planet, and prevents irradiating heat into space and keeping it on Earth and raising temperatures and wreaking all sorts of havoc. So that's one of the issues this aims to address. The second comes down to pollution and contamination in both our living spaces and therefore our food and water supplies, as well as the broader ecosystem and environment. This does come down to our own, what we as individuals are polluting and contaminating, but for the most part, this is a consequence of industrial scale manufacturing that produces most of the waste, or at least the largest scale of the waste. And this leads to the destruction of ecosystems and wildlife, again, including essentially our own living spaces. And it does go even beyond just survivability of ourselves and other life on the planet, because if we leave these issues unaddressed, this also leads to serious economic and social catastrophes, which is also quite bad and can make life hard for a lot of people. So now we can start working through this a little bit more specifically. Again, apologies. I've been a bit sick recently, so I'm a bit parched. The first thing we'll talk about in a bit more detail is the issue of climate change. So in general, nanoparticles are being developed to reduce greenhouse gas emissions, and that can be done basically one of two ways. The first is by helping to reduce greenhouse gas emissions in the first place. So for example, nanoparticles can be added to fuel, which encourages better air to fuel mixing and again enhances reactivity. So this leads to more complete combustion, better combustion, and just more efficient use of each unit of volume of that fuel. So if we are using less fuel, we're putting less greenhouse gases into the atmosphere and helping to combat climate change. The second example is what's known as carbon sequestration, which is carbon capture. It's essentially the process of either taking carbon in industrial manufacturing that's going to be released to the environment and capturing it before it has the chance to enter the environment, or taking carbon that's already out there and trying to remove it. And again, this is being done many, many different ways, or trying to be done many different ways, including with nanotechnology. But these nanomaterials can convert carbon dioxide and potentially some of these other greenhouse gases into all sorts of other useful things, like alcohols, for example. And again, just to highlight sort of the potential in terms of the category, they can be simple chemical catalysts. These can be photochemical catalysts that require sunlight to work, and so on. Next, moving from climate change to water treatment and purification. Again, clean water is just becoming ever more prevalent. I think it's only about 3% of the water on Earth is actually fresh water, and the rest is salt water. So it's not just uncontaminated water, but it's desalinated water. So both for cleaning water with contaminants as well as desalinating water, just to have fresh water, these technologies offer enormous potential. So this includes also industrial pollutants. Oil spills is one that I'm sure we're all sadly too familiar with. We have naturally occurring pollutants, which I'll talk a little bit more about later. Really any type of pollutant in water, including just salt, can be addressed with these technologies. And again, this is performed a number of different ways. The main exciting direction here is with what's known as nanomembranes. So these are membranes that we might see for filtering coffee or many other things. just on the nanoscale. So the actual size of the pores or the holes that's allowing things to transfer from one side to the other are on the nanoscale, which means that anything that gets through is essentially just water molecules, and anything that stays is essentially anything else. So it's very useful for that regard. And nanoparticles also are very good at adsorbing different other materials. So it's essentially getting them to stick on the surface. So that way you can sort of collect everything that you're looking to collect, all of the contaminants, and then easily separate them. Similarly, we have air purification, which in principle isn't too different than water. Of course, the details vary a bit, but it's essentially grabbing all of those contaminants and pollutants and just removing them from the air, capturing them, separating them, and disposing them one way or the other. So nanotechnology can be used to remove all sorts of toxins from the air. And again, another few examples. In the case of waste gases from industrial manufacturing, again, many of these processes produce all sorts of very toxic gases, and that's whether we're talking about climate change or we're talking about things that are acutely dangerous for human and animal health. So one option is actually taking these gases and using nanomaterials to produce carbon dioxide instead. And you might say, well, weren't we just talking about combating climate change? And yes, but if we are talking about the difference between carbon dioxide and something that could poison many people, carbon dioxide is still the favorable alternative. The second thing is that we can also try to capture that carbon dioxide right as it's produced, so that we don't have the issue of contributing to climate change in the first place. And this is something we do now. The problem is traditional methods are very expensive. They utilize chemicals, which create their own environmental problems, and they're uncompetitive, at least at scale. So they're unable to really compete in the market and be economically viable. The second thing is using ultra-thin nanoscale polymer films that can filter out the CO2. This is essentially this is a derivative of the first point. So again, if you're in industrial manufacturing and you're producing large amounts of CO2, this is a way of simply separating that carbon dioxide for easier capture or potential use. So this could be used, oh, sorry. There we go. This can be used to treat large gas streams under low pressure, which is something, again, quite common in industrial manufacturing. And this includes carbon dioxide, and particularly could apply to coal-powered fossil fuel plants, which is among the most polluting of the fossil fuels. And then a third concern is in the case of volatile organic compounds, which are often known as VOCs, which present a massive problem or hazard for air quality, particularly in the form of smog and ozone. And to take a moment to talk about ozone in particular for a moment, first of all, there's a few things to note. One is that most people think of ozone just as the ozone layer high up in the atmosphere that's protecting us from potentially dangerous ultraviolet radiation, and that's true. But actually, when ozone's much closer to the surface level of Earth, it's one of the more concerning pollutants. So ozone is good if it's high enough up, but it's actually quite bad if we're talking about the lower atmosphere. The second thing to note is that another part of our climate struggles that you all might be familiar with that was more prevalent several decades ago is the destruction and depletion of the ozone layer. So essentially what was happening is we were using a type of chemical called chlorofluorocarbons that were used in refrigerators and hairsprays and all sorts of these different products. And they were following use, escaping into the upper atmosphere, and they were reacting with ozone to break down the ozone into oxygen and these other atomic and molecular species. And over time, this was eroding the ozone layer and opening us up to be vulnerable to harmful UV radiation. The point is, though, that the world got together, they identified what was causing this problem, and we were able to essentially get rid of that chemical, develop a substitute, and here we are today, several decades later, at the point where those chemicals haven't been used for a while, and measuring the ozone from that point is the ozone layer has been able to largely recoup and repair. So the point is, these problems are addressable. We absolutely have the ability, or certainly will in the near future. And it really comes down to just working together and us as individuals basically calling to government officials, scientists, policymakers, doing everything that we can to try to get things done because we have the technology, we have the brain power. This is something we can do, and the story of the ozone definitely highlights that. Then we have just broader environmental contamination, which may include one or more of the things we've talked about and we'll discuss. So this is just decontaminating the environment. Again, oil spills or improper waste disposal or the aggregation of large, densely populated cities, littering, or so on and so forth. Um, so this goes back to the nanomembranes for the separation if we're talking about water and particularly groundwater, fresh water. But this also can include radioactive waste. So whether it's for nuclear disasters like Chernobyl in Ukraine or Fukushima in Japan, or so hopefully none of the future potential nuclear disasters, nanotechnology offers enormous potential to address radioactive leak or waste disposal. Another example is recycling. This one's a little more indirect, but for example, battery recycling and a lot of electronics in general are very difficult to recycle. The process of recycling is very hazardous for the people who are involved in this work. It's a lot of really nasty stuff. It's heavy metals, cadmium, mercury, lead, very carcinogenic, very dangerous things that are bad for the people who have to directly deal with the problem and bad for the broader environment. But many of these technologies, particularly batteries, can be made from nanomaterials instead of the many ways we make these technologies today. And the more that we do that, the more recyclable these materials will be, the less materials we have to use in the first place, which is something we'll talk more about. So in terms of reducing, broadly speaking, contamination, the more we use nanotechnology and nanoparticles, the easier we can recycle and the less waste that we can put out to the environment in the first place. And just giving another example, there's something you all might be familiar with called the Deepwater Horizon disaster, which happened in 2010 in the Gulf of Mexico. And this is considered to be the largest and the worst oil spill in the history of the petroleum industry, which sadly is saying something. And sadly, this technology wasn't developed at the time, but that disaster provoked a lot of scientists and researchers to really place more of an emphasis on trying to use nanomaterials to clean up oil spills and related disasters. So following this disaster, for example, one group of researchers developed a nanogrid of photocatalytic copper tungsten oxide nanoparticles, which is essentially just saying a grid of these particular particles that are made of this material that are photoactive. So essentially what they would do is take these particles, place them in the oil spill, and then with light hitting them as well, that would catalyze or provoke the reaction, and it would provoke the oil to decompose into different parts that were then biodegradable and could just be left alone and incorporated into the environment naturally. So from oil spills to electronics, there's a lot of potential for these materials to help decontaminate polluted ecosystems. We also have what is probably going to be one of the more important parts of this puzzle, which is nano-enabled sensors and real-time monitoring. Because what it comes down to is, while being able to clean what's already in the environment is great and very important, ultimately we should try to get to the point where prevention and control are the main priority. And so we can stop these issues. We don't want to have these challenges in the first place. It would be the goal. So a lot of nanotechnology enables really, really good, really accurate sensors and real-time monitoring that can easily detect chemical and biological contamination at very low concentrations. So oftentimes what will happen, again, whether we're talking about something from industrial manufacturing or something completely different, it starts with a trickle. It starts with a small leak that might somewhat suddenly grow not so small. So the earlier we can detect these things and do something about it, the less of an impact these contaminations will have for the environment. And here I just made a note that all of these technologies happen via so many different pathways and mechanisms. So sometimes it's photochemical, sometimes it's photoelectrochemical. There are so many different parameters, so many different knobs to turn. And again, this is all really in its infancy. So we're going to see so much more of this in the coming years. But for the time being, we're still struggling with a lot of the fundamental aspects. Another example is sustainable energy. So there's a lot of interesting advancements here. One of the most notable, where there's been a lot of buzz, is in the case of solar cells and photovoltaics. Previously, like if you see a solar panel today, it's almost certainly going to be made of silicon in one form or another. And those silicon solar panels have gotten pretty cost effective and fairly efficient. They're quite good, but obviously we want to make them better and better. I think the best commercially available solar panels today are at something like 18 to 24% efficiency. So while that's very good, of course, we'd like to get as close to 100% efficiency as possible. Um, and there's many different nanomaterials that offer entirely new designs to making photovoltaics and solar panels that might be much more efficient, much more cost effective, much easier to manufacture, or some combination. This also applies to fuel cell technologies and energy storage technologies. So if we're talking about energy storage, again, batteries, nanomaterials are a very exciting way of considering new battery technologies, which is something we need to care about more and more as we work on sustainable energy and electric vehicles and all of these sorts of things. And then we also have fuel cells. So part of combating climate change is moving away from fossil fuels entirely, not just making them more efficient. So one very exciting direction is in the case of hydrogen fuel cells. So this is essentially using hydrogen instead of fossil fuels to combust, for example, in an engine or for manufacturing purposes. And the source of that hydrogen, many people hope at least, is water. You can take water and through a number of different ways, you can break water down into hydrogen and oxygen, and then you can take that hydrogen that you've just made from the water and burn it. So ideally, water fuel cell cars and so on sounds like a very nice future. So hopefully that will come to fruition. Um, Again, solar cells I talked about a little bit. Another interesting example is in the case of even wind energy. And when I first learned this, I was confused for a moment because it's not exactly clear how nanomaterials might help wind energy. They seem a little bit unrelated, but the main way it's able to do so is in design. So for example, one of the most painstakingly, carefully designed aspects of a windmill is the turbines. The shape of the turbine, the material that it's made of, the coating it has on its surface, all of these things contribute to how efficient the turbine is at essentially at rotating, turning a turbine and generating electricity. So one example of this is in the design of these turbines. First of all, nanomaterials can contribute to making very, very light materials, which makes the windmills more efficient. But beyond that, it also can serve as a coating to prevent, for example, ice formation. I know a lot of the wind energy, for example, in Europe is in the northern part of the UK where it can get very, very cold, and you can have ice form on the blades of these turbines, in which case you're weighing them down and you're making them less efficient. So nanomaterials have the potential to improve the design of these turbine blades as well as many other things just to improve overall efficiency. And then this I already talked about a little bit in the context of new fuel cells. I'm just really excited, and there are certainly many other researchers excited at the prospect of not just replacing fossil fuels with something else, but potentially even water. So it's a very exciting direction. Um, and then talking about prevention and preparedness, again, talked about this a little bit, but nanotechnology also offers the potential to prevent the challenges we face in the first place. It's not just about sort of letting it happen and then using technology to get out there and fix it and then play that game forever. The ideal is that we can use these technologies to fix our current situation and then prevent it from ever happening again or anything like it happening again. And this takes several forms again. One of them is actually another interesting topic in and of itself, which is naturally occurring pollutants. Because when people think of pollutants, we typically think of the things that we put out there that are dangerous for ourselves and other living creatures. But there's also plenty of naturally occurring pollutants. Heavy metals naturally occur in the earth. Again, mercury, cadmium, arsenic. These are all things that are already present in different amounts depending on where you live. So if you live in an area with a lot of some radioactive material or carcinogenic metal, it would be great to use these materials to remove them. Another example, again, that I don't think can be emphasized enough is recycling, and specifically in terms of batteries, and electronics. This is just going to become more and more and more important as more of us have more electronics. It's not even it's more people in general having access and having more of them, especially as they grow in sophistication. So the ability to recycle these efficiently, and even in cases where these aren't recycled promptly or at least efficiently, these materials only having limited potential to damage the environment is quite good. And then in general, we also just have reduced material consumption. So again, whether we're talking about TVs or something else entirely, we can use less and less stuff essentially in the first place, which is always good. It's cheaper, it's quicker, and there's less stuff in the first place to pollute the environment. But there are many, many, many challenges, sadly, as with any exciting technology, there's always a catch. And the catch here is we're just not there yet. I mean, nanoscience and nanotechnology is helping many people in many different ways already. But it's specifically in terms of the environmental applications, this is just getting started. So again, it's in its infancy. In general, the two largest issues have to do with the cost. For now, most of these very exciting materials and systems are being made in the laboratory in very, very small batches in very, very controlled environments. And it's another challenge entirely to go from the laboratory to the chemical manufacturing plant or where these technologies are manufactured with these materials. So being able to do this cost effectively is a major challenge. And then even putting costs aside, just being able to produce enough in a timely manner is also a major challenge. So those two are sort of compounding challenges. And then a very key thing to note that I'll talk also more about is the health and safety concerns, because we humans can be a little bit ridiculous sometimes, where we rush to address a problem, and our solution to the problem just becomes the next generation's new problem. So we want to be careful that by deploying all of these solutions, we're not just creating a new and potentially worse problem. So we need to be very careful, especially in terms of health and safety. And again, I have this slide dedicated to that for the same reason. Again, the same properties, nanomaterials are useful because they're so highly reactive and they have those quantum effects. But those things that make them beneficial for so many applications also make them very scary for us. So you can imagine if you have these very highly reactive particles that go out into the environment, enter the water table, and then enter us, and now we have these very highly reactive particles inside us. Obviously, it will depend on the size and the shape and the material and so on, but there's a lot of potential for it to be a very serious health and safety hazard, similar to how, for example, plastics and microplastics have been over the last several decades that we're also just learning more about. So there's a very, very high importance to responsibly deploy and develop these technologies. And then looking forward, again, in general, nanoscience and nanotechnology offer great promise. And just as a reminder, this is a subset of a subset. So we have nanotechnology, which has all of these amazing things it can do. And then within that, we have environmental science. And then within that, we have each of the things and certainly many more that we've talked about. So it's very exciting. I would argue particularly environment, even though not yet, because it really can help to protect, rehabilitate, and preserve the environment. So again, it's frustrating as individuals and citizens of the world, because we're sort of victims to whatever our policymakers, government officials, scientists, and so on are going to do. So the best thing that we can do is stay informed and be knowledgeable about these topics, which is great. That's why we're all here today. And try to communicate these ideas and push the people who do have the power and the influence and the ability to make this change, make it actually happen. So thank you very much. Again, hopefully we have plenty of time for the questions. Just in case, if there's something you either don't feel like asking right now or may think of later, you're very welcome to email me. I'm always available. I'm not always quick to respond, but I'm always available. I will get back to you. So if you have anything on your mind, any questions, anything I can help with at all, please don't hesitate. You can email me here. So thank you for listening, and I look forward to hearing your questions.
Uh, I am very, very delighted, Tyler. I really feel full about a topic which I was not at all knowledgeable about nanoscience, nanotechnology. I believe, pretty much like you pointed it out, that's the trend of the future. But personally, I didn't know anything about it. And I am happy that I had that opportunity to listen to you. And we have the recording, and I anticipate I'm going to be looking at that recording from time to time so
Mhm.
that I can refresh my memory whenever necessary so that I can absorb the concepts that you've shared with us, with our participant, with our community. And I thank you very, very much.
Of course, thank
So,
you.
okay, ladies and gentlemen, the floor is yours this time. uh, Gleckler has made it possible for all of us to hear about those critical concepts or very important information. And if there are any aspects of that that you do not quite understand, it is your turn right now to raise your voice and ask questions. Our presenter has also been kind enough to share with the community his email address, which you can now see on your screen, which means at any point in time that you say, hey, nanotechnology, there is something that I forgot. And even if I reviewed the recording, there are some segments of that presentation that I still do not quite understand. So there it is, our presenter's email on your screen right now. Make sure you reach down to Gleckler and ask questions about anything that you do not quite understand. So I am now watching the whole room to see if there are any hands up of any participant, any attendee ready to ask questions. I haven't spotted any as of yet, but let me ask my own question since I am a little ignorant on this topic, Tyler. So I hope you will allow me, I am a participant as well, you will allow me to ask my own question.
Of course.
Uh, I love the idea of the fact that that is the trend of the future. However, as some kind of opposite idea, so to speak, that you also expressed, we don't know exactly what's going to happen in that future. You know, I love a particular illustration that you provided when you said, very often as we try with science and technology to resolve a critical issue, we end up creating a new one. So how do you see that, Tyler? Let's say for what may happen. They're talking, for example, about the possibility of some type of nuclear war, the third world war, so to speak. Anything that can happen. Is that nanoscience going to be a way to resolve those potential problems? Or is that nanotechnology or nanoscience going to bring some more problems to the point that living on this earth might be impossible? What is your take on that, Tyler?
It's a big question and a difficult question. I'm overall pretty optimistic.
Uh-huh.
History never repeats, but it rhymes. Definitely a believer in that perspective. So I think what will happen is after enough time, this technology will be very good and will help a lot of people. It will help all of us, really. It will just benefit the globe on the whole. But inevitably, there will surely be disasters and mistakes along the way. I think it's going to be overall a force for good because, again, the potential is just so much. And We don't, there's a lot more to learn about the dangers, but we're not totally in the dark. We do know, have a decent sense about the direction it's going, and for now there isn't too much to be concerned about. The main reason for concern is just the principle. It's about whenever something's new, even if we look at it now and go, I don't really see a problem, there's always a problem eventually. So it's about just keeping a skeptical eye and watching it carefully and not thinking we know it all. But that being said, I am optimistic that we will resolve the problems that we do have with it now, and it will get far better than we could probably understand in this moment.
Wow, I am impressed. That's the best way to address that topic, being optimistic to the fullest extent from a very spiritual point of view. This is the way to look at the future and, be on the positive side of it and think that everything's gonna play out well. Thank you for that response. Again, I want to remind our participants, our attendees, that the floor is now open to them. If anybody is maybe or forget, if anybody forgets how to do that, it's a matter of just going to the bottom of your screen where you see a horizontal menu with different icons. And I'm pointing at the one that reads reactions. All you have to do is go and hover your mouse around that reactions icon. As soon as you do that, you're gonna see some yellow icons, and one of which is a hand. And you click on that one, and we all will see that you want to ask a question, pretty much like Safia wants to do it right at this time. Go ahead, Safia. The floor is yours now.
Thank you, Dr. Valsin. Thank you, Taylor, for good presentation. I am our student for AIU. I am graduated 2014 for the university. Just it's not a question, just is advice. We understand the environment now is very corrupted. And we face, especially African country, the people with hunger, because of the no rain, the environment is desert. So that if this technology is good, why do not share with that country like East African and other? Because even America, the environment is more polluted with the industry. So if this is the solution, we need to advocate itself and the credit for the AIU University. Thank you, Doctor.
Yeah,
Welcome.
it's a very good point. The real shame, and the thing that I think the United States and the European Union and a lot of Western countries deserve a lot of criticism for, to put it mildly, is that these are the countries that are disproportionately responsible for climate change. This is where the bulk of a lot of the manufacturing is. The United States, and again, the European Union and so on, are largely responsible for the many problems, if you're asking me. So I completely agree with you there. And the main problem is that the technology for anyone, for anywhere in the world, just isn't quite there yet. I certainly would agree, though, that the moment that we have these capabilities, that we can produce enough of these materials and be confident that they're not going to be sent over to where they're needed across the world, and then again cause a bigger problem than is already there currently. So I do think aid and cooperation and collaboration is a key part of this, because we're not looking to, we want to clean up and repair and preserve and benefit everybody. I mean, I think anybody who's feels strongly about sustainability and environmental science would say the same thing, because it's not just about the United States or Europe or so on. And I hope that the legacy of those countries prioritizing themselves over the global community is not something we're going to see on this front. And my optimism on that front largely comes from speaking with and knowing and previously being one of the scientists involved in this work, and I can tell you that everybody is deeply committed to seeing this rolled out at scale for as many people as possible. And I'm not sure that was the case with previous generations of scientists. Maybe that's just my own bias, and I am an optimistic person, but I hope that the whole world will really be able to benefit meaningfully from these technologies.
Thank you very much. That's a very pragmatic response, Tyler. You emphasize the need for cooperation and collaboration from everybody. And you made it clear that everybody is indeed committed to protecting, to seeing the world improve in every aspect. So let's just keep our fingers crossed, hoping for that collaboration and that cooperation to happen very, very soon. So all of us in this planet can largely benefit from the outcome. Thank you very much. Now, Mike Biowa Mangon has his own question. Go ahead, Mike Biowa. We are ready for your question or comment. Mike Biowa.
Thank you, sir, for a great opportunity. I will have two questions, one for you and one for the professor presenter. The presentation is very unique, and I'm excited to hear that such a beautiful words on our environmental. How can we save the environment that we are in for the 20 years to come, for 100 years to come, for the generation that coming up, and also for the generation that are ending with them witnessing how the environment is affecting us. So my question to you, sir, in the protecting our environment, you know, let me start with Africa, where there are different countries have been misled by their leaders, and the other country in Africa are struggling up with the small technology to benefit their citizens. When we come to renewable source and non-renewable source into environment, so we have a country that did not yet utilize the renewable source to have environmental protection. What are the role for the United Nations, European Union on the 17 of United Nations goal? So how can this country can be held out to have a technology that help the society and feed the entire population and then help protect the environment?
Yeah.
Second, to my professor, the host, sir, you mentioned a lot the class life. I don't get any single life on my email. And the other things, my tutor is not connected me to know the specific subject that I'm in this term. So when the term is ended, I know myself that, okay, these are the subject that I studied this term or the module that I'm in, so that even I can have a briefing of studying, regular study. So I see the presentation, but I'm not getting it back, the presentation. So what does that mean? Thank you, sir.
So I can take that first question, of course. In terms of the role of the UN and these other bodies, that is something that I know very little about, frankly. So I'll give you my opinion and my best sort of analysis, but I'm frankly not even sure exactly what each group is supposed to be doing, when and how. The best thing I can say to that question is essentially that the point of the UN and these other organizations and institutions is to actually see some results, to actually facilitate cooperation and collaboration and so on. And as you said, a lot of countries throughout the world, in Africa, have yet to even be able to utilize a lot of the renewable sources that they have at their disposal. The thing that I hope nanotechnology will enable is not just taking people who already have access to these different technologies and improving them and making it more cost effective and so on, but hopefully this will make it easier for countries that have yet to realize the full potential of their renewable energy sources and of their resources in general, and make it easier to leverage it. And hopefully that will manifest in the form of the citizens, because the easier it is, the cheaper it is, the better and easier people can start businesses and start creating their own engineering solutions and so on. So I think the lower the barrier to entry and the easier and the better the technology, the better it will be for exactly what you're getting at. Again, in terms of what the role of the UN and related bodies is, it's hard to say, but I certainly hope that they are using as much power as that they have afforded to them to try to drive an equitable future in this regard. Because as we keep touching on, the problem is there's one group of countries that sort of create the problems, and then that's the same group of countries that create the solutions and then don't share the solutions. So it's not fair whatsoever for the global community for all of this technology and accessibility to be localized in the hands of a few. So I would say the big role of the UN is to facilitate as equitable as a future as possible using these technologies. In terms of the courses and the live, though, I have no idea.
Thank you very much, Mr. Gleckler. Now, part of the question from Macbior Mangan pertains to me, the host of this event. Thank you for your question, Macbior. Pretty much like you said, I usually emphasize that we all enjoy those live class sessions. And if I understand you correctly, it looks like you are not getting any live type of interactions. Let me say two things about this. Number one, personally, as an advisor, if I look at my list, I certainly do not have you in my roster of students. But as an advisor myself, I stand behind every single student that I deal with. And what this means is I am available 24 hours a day. Anytime you send me a question and you want a live conference at any time, if you want me, let's say, I know there is a huge difference between our time zone here. I am in North Miami Beach, Florida, and your time zones, those of you who are in Africa, in Asia, Europe, and so forth and so on. If there is a request for me to join you at a time that is the equivalent of 2 a.m., 3 a.m. On my end, I will respond. There is absolutely no request from my students which I do not fulfill expeditiously, rapidly. So that's one aspect of the question. When it comes to whatever may happen in terms of the availability of those live class sessions, what I understand from our technology department is that all students have been informed. They've been advised about the time of the presentation and so forth and so on. And then also the session, all sessions are recorded, and a link to those recordings is shared with students. If you do not receive that link, if you don't see it on your portal, I would recommend that you get in touch with either your advisor, and I have no doubt that they will respond to you immediately. So please just be patient and contact those people. And I'm going to relay that as well to other authorities of our school. And the satisfaction of every student is our key goal. We're not getting into the details about that, but that's exactly what we will do, what we've been doing for about nearly a quarter of a century, and that's what we will keep doing. All right, now going quickly to Chris. No, Chris comes after Lombayi Ilonga. Go ahead, Lombayi. We are with you now for your question or comment. Lombayi. We are not getting Lombayi. Let's try again. No, it looks like the audio settings of Lombayi Lunga are not set properly. So we will wait, Lombayi, until we can connect with you. But we also have a hand up from Chris Akote. Go ahead, Chris.
Yeah, thank you very much for the opportunity given to me. Tyler, you've done well. Actually, we, the Africans, we need this technology, but not, I don't think America needed it at the moment, because Americans, they have all the knowledge and ideas about the things that Tyler is talking about already, but implementing it is their problem at that area. All right, in my case, Doc, I am struggling with my scripts, like in terms of my course. I'm doing clinical psychology, but I receive different courses, emails that I have no idea about. And I think I received an email that I am in phase 2, how to complete it. But for some time now, I've been on phase 2 for a long time, and I don't get specific courses pertain to my course I'm doing, like clinical psychology. I'm not having an idea about any of those things. So if you can please help me a way out. Thank you.
When it comes to this, that's a question that doesn't go to our presenter, Tyler Gleckler. What I would like to ask every one of your, every participant, is to kindly, let's say, send questions that do not pertain to nanoscience and nanotechnology, the topic being addressed by our presenter, Tyler Gleckler. Send those questions, please. I'm begging you to either the tutors or the advisors, and there is no doubt they will address those questions as soon as they get into their inboxes. So far here we are talking about nanoscience, nanotechnology, and particularly the use of that science for environmental repair and preservation. So please, let's, I hope you agree with me, Chris, or if you don't mind, let's say you can either send me that question to myself. That is Dr. Vaccine at aiu.edu. As soon as that question comes to me, even if you're not a student on my list, I will respond to you, Dr. Vaccine at aiu.edu. All right, so let's now try Lombayi Ilunga. Are you ready now to ask your question, Lombayi? No, Lombayi is not ready as of yet. So let me quickly jump onto the chat line where I saw a question a short while ago. Let's see. That question is from one of our students. I'm trying to get back into the name, but it's a question for you, Tyler. Make sure all the questions go to our presenter, Tyler Gleckler. The question is, what about the risk of that new science? I think that you have addressed that to a certain extent, Tyler, but remember, ladies and gentlemen, the recording will be sent to you or placed on your student portals. You can just go back and look at everything that happened during that presentation. But let me ask you, please, Tyler, to allow me to ask you to briefly address that again, the risk of that new science base?
Yeah, of course. The biggest risk is just that we don't know what we don't know.
Okay.
So for the moment, we don't have too much of an idea about, oh, it's going to cause cancer or it's going to be bad for this animal or these plants. We just know that there's so much more left to learn that there's got to be something that poses a risk. That's the first thing. The second thing is, as I said, the particles are so useful and they can do so many amazing things, largely because they're so reactive and that they have these unique properties. But you can very easily imagine the same thing that makes them so great for again, biomedical applications to entertainment and so on, is the same thing that could make them very, very dangerous, because typically very reactive chemicals or species that enter our body can do a lot of damage. I mean, even if you take the example of radiation and why radiation is so dangerous, what actually happens when you're exposed to radiation, the reason why it destroys the DNA in our bodies is because it actually is first affecting the water in our cells and makes these very, very reactive chemicals that then interact with the DNA and can do tremendous damage. And then that causes cancer and so on. So you can imagine it would be very different as compared to something like radioactivity. But when you have these very small, very highly reactive species, it's very, very difficult. And they're also very, very tiny. So in a world where we start deploying these and spreading them all around, and then we go, uh-oh, we should roll this back. Let's go clean up what we've put out thus far. They're so small that it becomes very, very difficult to do anything about it. So before we put it in the environment, we should just be very, very careful, done all of the testing, done all of the checks and balances just to make sure that it's okay and it's not going, if there is an unexpected side effect, it will be somewhat contained.
All right, thank you. I have a question of my own right now, and please forgive me because this is not for me, this is for our participants, your presentation, but of course, I am also a participant. Forgive me as well for being a little ignorant on this topic,
No
which
worries.
kind of is compelling me to try to get deeper into this. And I recall you mentioned problems that can occur about climate and the ecosystem. I don't get that idea very, very well. I realized that, let's say, about 2 weeks ago, we had some heavy rains here in Florida. We're talking about the month of April, when those rains started. And I don't remember having seen rains, in the last 30, 40 years in Florida in the month of April. We're talking about heavy rains, heavy downpours. So is that really linked to some kind of degradation or problems with the ecosystem? And what is the role, the function of nanoscience to either resolve that issue, or whether we could consider the nano elements to be responsible for that kind of climate change? I don't know.
Yeah, so the first thing I'll say is the main difficulty with climate, and I think one of the reasons there's always so much ongoing debate, is that it's very difficult, and it's difficult in a way that's not unlike physics or most parts of chemistry, because we're talking about, it's so complex, so many things affect so many other things that it's very, very hard to trace down exactly what's going on. That being said, there's very good reason to believe that, yeah, the things we're seeing in terms of climate change, or formerly global warming, is affecting that type of rainfall. However, again, it becomes very dicey, because to say that global warming or climate change is responsible for specifically what you're referring to in Florida, maybe yes, maybe no, maybe a little bit, maybe a lot. That the specifics are hard to say, but in general, if we do see a consistent increase in the temperature, for example, we will see more and more evaporation from the oceans and from other bodies of water. And if we have more and more moisture in the air, we're going to have more and more rain. Another consideration is when you have a lot of pollution, the way rain actually will form is oftentimes you can provoke rainfall with by providing very, very high surface area, small surfaces for the raindrop to actually coalesce and then fall. So actually sometimes higher amounts of pollutants can provoke and encourage rainfall. And these are just two examples. So yeah, and in the context of whether these technologies are to blame for a lot of what we're seeing, I would confidently say no, just on the basis of, again, this is so new and so little of it is actually out there in the world, that it seems to me unlikely, unless there's a lot that we don't know, which is always possible, that it's responsible for a lot of the climate and ecology issues. And then to answer the last portion of your question in terms of the ecosystem and the environment in general, again, some of the most densely populated places in the world, both for humans and a huge number of animals, are along the coasts throughout the world. And if we do see notable sea level rise, a lot of those places will no longer be there, and neither will the homes and ecosystems for these plants and animals. So there's so many different things going on, and again, it's such a complex topic because it's very hard to link one thing specifically to another. Everything is affecting everything else, and you have to perform these studies very carefully. And you can't just go in the laboratory and do an experiment. You have to wait for a whole season to go by and collect the data, and wait year and year and year. So it's much more difficult than a lot of other branches of science.
Thank you very much. I think this was the last comment we had about this awesome presentation of Tyler Gleckler on the topic of nanoscience and nanotechnology. Remember, ladies and gentlemen, the session was recorded, and the recording will be sent to you through email or via your student portals. And also, the presenter's email is still on your screen right now. You may feel free to send questions to him about any aspect of that presentation which you may have missed. So I want to thank everyone who was in the audience, electronically, of course, remotely, through Zoom to attend this outstanding presentation. And let me turn the floor back to you right now, Tyler Gleckler, for your last comments, please.
Just want to say thank you. It's just really cool to see people take an interest in this type of thing. I think it's really important. I think it's really interesting. So thank you all for coming. I hope it was interesting. I hope a few of you here were people who came to the last call, the last talk, and enjoyed that one, so came to this one. And hopefully I'll do them in the future. So thank you again, and I'm here for anything you might need.
It's been a real delight, Gleckler. Thank you very much. And I'm saying this on behalf of Atlantic International University. The microphones are on right now to the entire group of participants who join us today. So let's together, ladies and gentlemen, acknowledge the class of that presentation and say thank you to Mr. Tyler.
Thank you.
Thank you, Taylor.
Of course, thank you all very much.
Taylor, goodbye.
Thank you so much, Taylor. Goodbye.
Thank you, bye.
Thank you, Doctor.
See you.
Thank you, Dr. Maxine.
Thank you, Dr. Tyler.
Bye-bye now.